Hey guys, what's going on? So we're continuing with conformal field theory. I realize I kind of put this on the back burner a little bit, but we're going to keep on getting into this. I've made a calendar for myself, and we're going to try to stick to this calendar as strictly as possible, where conformal field theory is going to be on Thursdays, and I'll announce when other topics are going to be played as well. And so without further ado, make sure to hit that like and subscribe button. You can go into my Patreon page and support there, or you can become a member here on YouTube. Again, this channel is all about deriving and understanding complex, difficult mathematical theories of the universe, everything physics, everything math, and we're going to get into some life sciences too. But again, make sure to hit the like and subscribe button. Now let's go ahead and get started. Again, also, when you contribute, you get access to what you see here, plus exclusive content. And that's going to be for everything, right? So if this is a flat rate, right? This is $10, and with $10, you don't just get the conformal field theory playlist. You get everything that I'm producing. It's just at a complete flat rate. That's $10. All right. Now let's get into it. Alright, so we are going to be talking about deriving the conformal algebra today and in the next video. So we are going to aim for a very interesting structure of algebra that we've taken all of these operators, right? So we have the translation operator, we have the rotation operator, we have the dilation operator, and the special conformal operators, and these generators, or operators if you will, are going to form something called the conformal algebra, okay? And that's going to be at the basis of conformal field theory, okay? So before we do this, let's get some useful identities out of the way first. The way we're going to do this is just by looking at these three identities. So we want to understand what the commutation relationship is between the position operator and the derivative operator, position squared and derivative operator, and then this weird mixed one, right? There's no comma here, no comma there. So, and then I'll change the thickness of my pen here. So let's go ahead and look at this one really quick. So this guy here is so x del, right? So x del, and then del x. When we take the derivative of this guy right here, we would take this is the product rule, right? This is the derivative of f times x, and then the derivative of x alpha. And we established this in an earlier video, how db or del beta x alpha, that's going to be our metric. Our metric, again, the reason for this is because we had alpha and beta when they're the same, then we're going to get some result out of this db x alpha, or del beta x alpha. When they're not the same, that's going to be like taking the derivative in some orthogonal direction, and we want that to be 0. So most generally, we call it, we're going to name it the metric tensor here. So we have this, and then this, we just get this, right? Because this minus this is just 0, so we get this. So that's one identity. Our one identity is this guy here is equal to this. So this commutation relationship operating on f is just equal to the negative of our metric tensor operating on f. F is, again, just a dummy function. All right, so let's take a look at this guy here. We want to understand this one. So we have x squared now. Well, x squared can be split up into dx alpha, or x alpha, with upstairs and downstairs, and then our del beta. And then just by rules of commutation relationships, again, we get from here to here, right? So this is going to be this guy, commutation of this guy multiplied by this, and then commutation of this guy multiplied by this. That's going to be this one. You can kind of see how this works, right? So I'm not going to dwell too much on this. Anyways, we have this term here gets to this term, and then we know what these guys are because we just established them over here. So, which was g alpha beta. So we have G alpha beta, and then this guy is going to be, this could be G also, but this could be G also, but we see here that this is going alphas. Remember G or G or the Kronecker or the Kronecker delta. This is just going to sum over indices, right? So this is going to sum over beta, and then alpha, beta, this guy, and so we get so we're going to get 2x alpha, right? Because this is going to sum over alpha, and then right. So this guy here is going to be x beta, right? This guy here, we're sum over alpha, right? So that's going to be x beta as well. And so that is going to, that should be a minus sign, so it's going to be 2x alpha. I think it should be a beta, right? That should be a beta. All right. Okay. And then this guy here, this is going to be, this is actually a dummy index. That's why I think I probably set that to alpha. Anyways, that's not going to matter too much. All right, so now we have this guy here. It actually probably will matter, but this is a dummy variable, which is why I probably typed alpha. And so we have this guy here then. So this is going to be dx mu, here's dx mu, and then x nu, right? And then we take our commutation relationships again. That's going to be g mu beta, mu beta, nu beta, and then again we're doing this sort of the same thing here, but we can't really sum over, right? Because these two guys are different indices, so we get this guy right here. All right, with that being said, our three identities are therefore this, where this guy was, again, these are all just dummy indices, right? So these are our three identities. Now this is what we're going to aim towards. This usually when you study conformal field theory, these things are just given to you in a list, and I took the liberty of sort of mapping them out, trying to put some symmetry to the picture here, just to get us to maybe understand this a little bit better, maybe keep it in our heads a little bit better. We have this guy here, which is our standard Lorentz algebra, okay, and then this we can take this guy here with the m rho sigma. Well, here's our m, right? Just different named indices. Okay, that's why I have an arrow going up to here. So this is going to feed in to this guy. We have our p mu. These are one of our conformal. These are one of our operators, right? This is our momentum operator, or something akin to our momentum or translation operator, right? So we have p, and then k is our special conformal generator, right? And that's going to be k here. So these two guys, one of these guys is going to feed into the commutation, and one of these guys is going to feed into the commutation. And then, and we have this guy, m, which is right here, and then d, which is our dilation generator. That's right here. And so I have that listed right here. And then this guy, one of these guys, commutated with d is going to give us 0. Right, so this is an algebra for our translations, algebra for our special conformal operators. This is the algebra for the translations with the special conformal, and then this is the algebra for our Lorentz operators and our dilation operators. And then we have m then is also gets fed into here, where we have p rho. So our Lorentz with our translation, Lorentz with our special conformal, and then our dilation So D with our... Hey guys, thank you for watching this shortened clip from a longer video. If you want to get the longer video, again, you can become a member of the YouTube channel here, or you can go into my Patreon page where you can become a member there. All the tiers should match up in price range, and yeah, if this is the type of topic you're interested in and the type of topic you want to contribute to, then please become a member, hit that like and subscribe button, and I'll see you guys in the next video. Bye.